All right, we're going to start chapter 5 today, gas laws. All right, so we're going to talk about gases. So we did the density of liquids and solids. We're going to do density of gases, but we're going to do that by the ideal gas law. All right, so remember, gases are compressible. So you have your gasoline engines, vaporizes your gas, you compress the gas, you ignite your gas. All right, so gases are compressible. Pressure, volume, temperature, and amount are related. All right, so we're going to talk about P, V, T, and the amount is moles. All right, and so you know the equation, it's coming up later, but that is pressure times volume is equal to moles, ideal gas constant, and temperature. So we're going to be talking about pressure, volume, moles, and temperature of gases. All right, so pressure, the force exerted per unit area. So that is force per area. All right, now when we get our pressure, that is going to be our density times gravity times height. All right, so pressure is density times gravity times height. If we do SI units, all right, so if we're doing our SI units for density, so remember density is mass over volume. And so for solids and liquids, we use in chemistry grams per milliliter. But again, the SI units are not grams for mass, it's kilograms. The SI unit for volume is not milliliters, it is meters cubed. All right, so the SI units are going to be kilograms per meter cubed. Gravitational force, 9.807. And that is in meters per second squared for the SI unit. All right, and then that's G. So that's gravitational force. I put it to 4 sig figs. It probably should only be to 2, but I'm giving it to 4. And then your height. H is height. And that's going to be in meters. All right, so when you put in your SI unit for the density, kilogram per meter cubed, and then you put in your SI units for gravitational force, meters per second squared, and you put in your SI unit for height, which is in meters, you get a kilogram meter per second squared. So the SI unit for pressure is a Pascal. So the SI unit for pressure is the Pascal. All right, so you have density, gravity, and height. So what you're going to do is you're going to have pressure is equal to pressure. So whatever your pressure is, that's your pressure, which kind of is obvious. But so you can use the density, gravity, height is equal to density, gravity, height. When we're going to do our pressure, we're going to talk about millimeters of mercury. All right, so we can also do it in millimeters of water. All right. The reason why we use millimeters of mercury is because the density of mercury is very high. It is a liquid metal. If we're looking at millimeters of water, it's more like, meters of water. You're going to have a giant apparatus to go measure how many meters high the water is. Whereas mercury, you can do this in your lab. You just see how many millimeters of mercury that has gone up. All right, but you could do it in water instead of mercury. Again, we picked mercury because of its high density and liquid phase. But what cancels out is the gravity. So gravity is the same whether you're using any liquid that you're using to measure pressure. All right, so the density, you would have, say, mercury on this side and the height of mercury on this side. Now on this side, you would have density of water, height of water. All right, and so you could, again, we're going to talk about millimeters of mercury, but you could do it at any height of any liquid. All right, so here are the units that we are going to use most often, and those are the atmosphere, millimeters of mercury. All right, we are not going to use the bar very often at all. Torr will be used, but these are the same. Millimeters of mercury and torr are exactly the same. If you don't like torr, right, millimeters of mercury, it's the same thing. 1 millimeter of mercury is 1 torr. All right, pascals is used sometimes and not very often. So again, these are the two units that we are going to use all the time. And what you need to memorize, and the only thing that you need to memorize for pressure and anything else that you need for pressure would be given. And that is that exactly 760 millimeters of mercury is 1 atmosphere. You must memorize this. All right, and you also need to know that a millimeter of mercury is the exact same thing as a torr. You need to memorize that as well. All right, so if the problem gives you torr, that's the same as millimeters of mercury. And 760 millimeters of mercury is going to be 1 atmosphere. When we do, PV is equal to nRT. You're going to have your pressure in atmospheres for the R value that we are going to use. There's 100 different R values. The one that I have chosen to use, the one the book uses all the time, the pressure units are atmospheres. All right, to measure the pressure of the atmosphere, we use a barometer. So if you go on TV, they'll say the pressure of the day is 29.92, which is horrible because they do not give any units. They just give a number, like everybody knows what that means. All right, so in the United States, whatever, we measure things in inches and feet. All right, so this is in inches of mercury. All right, so when they give the pressure of the day, if you watch TV, go to the weather station, they'll say the pressure is 29.92. This is a normal atmospheric pressure. All right, and that is in inches of mercury. Maybe online they would label it as inches of mercury, but normally they just give the number. All right, so that's a barometer that you can measure the pressure of the atmospheres. Now, if you have a manometer, this is for measuring gas pressure in a vessel. So you're in lab, you got your gas in this vessel, you use a manometer to find out what the pressure is of that gas. Or a liquid with a high vapor pressure. So if you're doing the pressure of a liquid, you're looking at the vapor pressure of the liquid. So it vaporizes. All right, so this is the example that I gave before. The pressure is the pressure. It doesn't matter if you're using mercury or if you're using water. All right, so the height of water, so if you were given the density of mercury, and you were given the pressure of mercury and height, like millimeters of mercury, that is a height of mercury, you will then be able to, and you know the density of water, you can look up, these are two constants, density of mercury, density of water. All right, and so you can solve for the height of water, and you will find that the height of water is extremely high. All right, and so we don't want to go climbing ladders to see what the pressure of the day is. We just want to stand in our lab and say, yes, it is 760 millimeters of mercury. All right. So empirical gas laws. So we are going to talk about Boyles Law, Gay-Lussac's law, Charles's law, and the combined gas law. So all gases behave quite simply with respect to temperature, pressure, volume, and the amount of substance, and the amount of substance in moles. All right, so when we do our empirical gas laws, two of these things are going to be constant. They are not going to change. then the other two will change. All right, so Boyles Law is what we're going to start with, and that is a pressure and volume. So when we do Boyles Law, we're going to do pressure and volume. All right, so that means that we have to be at constant temperature. That also means that we cannot change our amount of gas. All right, and so here is Boyles Law. And so Boyles Law, you simply have a piston that has a gas inside. And if you increase the pressure, all right, that means you're pushing this piston down. You see that we have a higher pressure. So this is a compression. So we compress the gas. All right, so what we see is we have a higher pressure, but we have a smaller volume. All right, so they are inversely proportional. If you increase pressure, you're going to decrease the volume. All right, if you increase the volume, all right, so if you increase the volume, so if we go the other way and we increase the volume, all right, so now we have our gas, same amount of gas is in there. We're not changing the temperature. So now here's the gas. So we have less molecules banging against the wall. All right, so if you increase the volume, you're going to decrease the pressure. So they are inversely proportional. All right, so if you increase one, you decrease the other one. All right, and so then that means that when we have our pressure times our volume, pressure times volume, that gives us a constant. All right, and that is the Boyles Law equation is simply P1V1 is equal to P2V2, or I is for initial and F for final, state 1, state 2, however you want to write it. I usually write P1V1 is equal to P2V2. That's the same thing. All right, so that's Boyles Law. So you need to know Boyles Law. Boyles Law, you have constant temperature. So constant temperature, all right, and it has to have a sample of gas that does not change. We are not injecting more gas. We're not pulling gas out. All right, so the amount of gas in this system is a constant amount of gas in the system. The temperature is not changing. All right, the only thing that we're changing is the pressure and the volume, and you need to know the equation. P1V1 is equal to P2V2. The other thing that you need to know is that the units, all right, they just have to be the same units for pressure and volume. So it doesn't make a difference what the pressure units are, they just have to be the same. Doesn't make any difference what the volume pressure units are, they just have to be the same. All right, that is not going to be true for all of these. This is true for pressure and volume. As long as they are the same, they will cancel. All right, so if I give you bars and I just said we're not going to use bars, and the question is what's the final pressure, you're given that final pressure in bars. So you don't need to know what bars is, but you need to know that in this equation, whatever the pressure is on this side, that's the pressure unit on the other side. All right, pressure versus temperature. Okay, so they're inversely proportional. Increase one, decrease the other. All right, so we have pressure using a manometer. All right, so the piston picture, this is the one that I will always use. All right, so here's your piston, here's your gas. We're not changing the number of gas molecules in here, 3, 6, there's 10 gas molecules. Here we have 10 gas molecules. All right, so when we increase the pressure from a 0.5 to a 1.0, so that is doubling the pressure. When you double the pressure, note what happens to the volume. It goes from 1.4 liters to 0.7 liters. So when you double the pressure, you half your volume. All right, again, you increase your pressure, and you can put that into P1, V1 is equal to P2, V2. All right, so if you put in your 0.50 atmospheres at a volume of 1.4, and then you said, all right, I'm going to go to 1 atmosphere. All right, so this is ATM, this is in liters, ATM, this is in liters. You could solve for it. Again, you're going to get 0.70 liters. All right, so you have one of these is going to be an unknown. So if it says you're at 1.4 liters and you double your pressure, what's your volume? Well, it's going to be half that, so it's 0.7. All right, so again, we are not changing the number of gas molecules. They are the same. We are not changing the temperature. It's at the same temperature. All right, so here would be a question. Volume of oxygen gas occupies this volume. So first volume I come to, I call V1. At this pressure, this is the pressure I will call P1. All right, and then they're going to give a temperature. As long as that temperature doesn't change, temperature remains constant, we're not going to use that temperature for anything. All right, so what is the volume if the pressure changes to pressure 2? Okay, what is the volume? Volume 2 is the question mark. P1 V1 is equal to P2 V2. You just put in your numbers. You have to make sure that your units of pressure are the same. You don't have to convert them to anything unless they're not the same. If they're the same, then you leave them just the way they are. The unit for volume, you know that we have milliliters, so our answer is going to be in milliliters. So you put in your pressure, 751 millimeters of mercury. You put in your volume, 38.7 milliliters. You put in your pressure 2, 359 millimeters of mercury. And then you solve for V2 by simply dividing by 359 millimeters of mercury. Divide by 359 millimeters of mercury. So now you see the millimeters of mercury were canceled. That's why the units have to be the same. And then the unit you get is milliliters. And so when you push the buttons, you get the answer, which is 81 milliliters. So again, 3 sig figs. Make sure you put your sig figs right. 3 there, 3 there, 3 there. The only correct answer is going to be given to 3 sig figs. Your calculator may just say 81. Make sure you put in the 0.0. 3 sig figs for your answer. All right, so now we're going to do volume versus temperature. All right, so we have the Kelvin. Remember, when we're in lab, we have our thermometers. Thermometers are read in Celsius. So you have to add 273.15 in order to convert that to Kelvin. All right, now absolute zero, when you have Kelvin is 0, all right, so you have absolute zero. Absolute zero means that your temperature in Kelvin is 0. If you solve for degrees Celsius, so 0 Kelvin is equal to minus 273.15. You put a 0 in here and you solve for degrees Celsius, it is negative 273.15. All right. So it is the temperature at which the volume of a gas is hypothetically 0. So nothing can exist once you hit the absolute 0. Everything stops, everything's dead, nothing exists. All right. So this is the absolute temperature scale in Kelvin, the lowest possible temperature. All right, so now we're going to use Charles's law, and this time we're going to have, again, the sample of gas. We're not going to change it. However many molecules of gas you started with, that's how many molecules of gas you end with. But this time we are going to keep our pressure constant. So we're going to have a constant pressure. All right, so now we're going to do a volume change. All right, so if you have your, let's do which one do we want to do? All right, let's say you have a balloon and you go outside. All right, so inside, let's say it's wintertime. So inside it's 25 degrees Celsius and it's freezing weather outside, and so it's 0 degrees Celsius outside. All right, so you should notice that. All right, so the pressure inside, pressure outside, pressure in Quincy is the same, whether you're inside or outside, unless you're in a pressure chamber. All right, so the pressure is the same, and we will say for argument that our molecules cannot go through. We have a Mylar balloon, molecules can go through very, very, very slowly, but I'm just saying I go outside and molecules just don't start going out of the balloon. All right, so it's just getting colder. And if you ever take a balloon outside and it's cold, it gets smaller. And that is Charles's law. All right, so as we decrease the temperature by going outside and it's very cold, you notice a decrease in the balloon inflation. And so a decrease in temperature is going to give us a decrease in volume. That is Charles's law. Again, if you were outside and your balloon looks like it's going flat, and then you walk inside where it's warmer, all right? So if you increase the temperature, you're going to increase the volume. All right, and sometimes if you blow up your balloon and it's very cold, and then you go someplace where it's very warm, that pressure may be too much for the balloon and it may burst. All right, so the equation for Charles's law is volume over temperature is equal to volume over temperature. This one is more difficult because I'm going to say that the volume units have to be the same. I am not going to say that here. So I'm going to write it. I'm going to say it 100 times, and nobody's going to do it. Well, some people will do it. Most people will not. All the problems are given in Celsius. And when you put the Celsius temperature in there and it's multiple choice, that answer is there. That is the wrong answer. Do not put Celsius in your temperatures. These must be Kelvin. You're going to think you got it right. Somebody will come in. I got every answer on this test. Yes, you did. Every wrong answer. These must be in Kelvin. All right. If you use Celsius, the answer is there. It is the wrong answer. All right. You have to have your temperature in Kelvin. Again, thermometers are in Celsius. All these problems are in Celsius. If you don't convert it to Kelvin, you have the wrong answer. You can never divide by 0. You have 0 degrees Celsius. That's a very common temperature. That is simply ice water. All right, that is the freezing point of water. You get that all the time. You stick that in there and your calculator can't do it because you can't put that there. It must be in Kelvin. 0 Kelvin, nothing exists. If you put a 0 in there, well, you can, maybe the hypothetical question is you're at 0 Kelvin. What's your volume? You can't have one. That's correct. Nothing exists at 0 Kelvin. All right, make sure you have your temperature in Kelvin. No other units will work. All right, so again, you can be cold by going outside. You can also be cold by putting it in liquid nitrogen. All right, and so the blue balloon, if you put that in the liquid nitrogen, it will shrink. And you will actually see inside of the balloon liquid air. All right, so you can liquefy air. And then, of course, as it warms up, then it blows back up to its normal size. All right, so that is simply, a balloon is a good example of Charles's law. It gets colder, it gets smaller. It gets warmer, it gets bigger. All right, so we're changing the temperature. We're changing the volume, the pressure of that day in that same room. That is the same. But your pressure is the same, and your amount of molecules in the balloon at a given time is the same. Eventually, they do escape out of the balloon, but that takes a lot of time. All right. So here we have. So when you have this picture, what you have to notice is what's changing and what's not. They may give you a pressure. As long as they give you the same pressure in the second part, we know that we have constant pressure. When it's not changing, that means it is constant. All right, so here we see that we are decreasing the volume. So we are decreasing the volume. All right, and so our volume is going from a, what are we doing here? No. All right, so we're just saying that right here. All right, so we're starting here. So this is your V1. Apparently this is going to be V2. This really shouldn't be here. All right, so that's V1, and this is T1. All right, so that's your T1. Now you come over here, and this is P1. Now you come over here, you have P2, and then you have V2, and then you have T2. So everything in the first one, I put a 1. Everything in the second one, I put a 2. And when I see that P1 is equal to P2, now I know I have constant pressure. All right, and so when I have constant pressure, I see that then I have to have things that are changing, and that is your volume. Volume 1, volume 2, different. Temperature 1, temperature 2, different. And so then you have Charles's law. V1 over T1 is equal to V2 over T2. and they give you all of the numbers. However, if you change this to Celsius, this Kelvin to Celsius, if you change this to Celsius, and you're solving for V2, that would not be your V2. All right. So when you go from 100 Kelvin to 200 Kelvin, you have doubled your temperature. All right. So you double your temperature. When you double your temperature, what happens to your volume? You double your volume. You increase the temperature, you increase the volume. You double the temperature, you double the volume. All right, so whatever the volume was, 0.26, great. Now it's 0.52. You double the temperature, you double the volume. All right, so here's the tricky part. The tricky part is you go from 100 degrees Celsius to 200 degrees Celsius. This is not doubling the temperature. All right, you have to, again, must convert this to Kelvin. So 273.15 plus 100, you're going from 373 Kelvin. And then you, instead of adding 100, you add 200 to 473 Kelvin. This is not doubling. 373 times 2 is not 473. All right, it's 700 and something. So you have not doubled your temperature. So that is a very commonly missed question. You'll look at that and you say, okay, I double my temperature, I double my volume, and you put that as your answer. Wrong. You're not doubling your temperature. Your temperature is only doubled when it is the Kelvin temperature that is doubled. Again, all of these problems, temperature must be in Kelvin. Some problems are given in Kelvin. Most problems are not given in Kelvin. All right, so this is a typical problem. You prepared carbon dioxide by adding HCl to marble chips, which is calcium carbonate. According to your calculations, you should obtain a volume, V1, of 79.4 mils of CO2 at 0 degrees Celsius and 760 millimeters of mercury. So here is V1, here is T1, and here is P1. How many milliliters, V2, how many, question, of gas would you obtain at 27 degrees Celsius? And so now you have a T2. All right. And this problem is in the lab. You are in the lab, and the lab pressure for the day is 760 millimeters of mercury. So P2 is also equal to 760 millimeters of mercury. We did not pressurize it. We didn't put it into a pressure container. We didn't put it into a piston. We are in the lab preparing our gas. And so our pressure is not going to change. All right, so the first thing you have to do, and if you don't, you get the wrong answer. Well, you would have a hard time getting the wrong answer for this one. All right, so if you recognize Charles's law, V1 over T1 is equal to V2 over T2. So you should be happy with a 0 degrees Celsius problem, because when you plug that in, the calculator says you cannot divide by 0. You are doing it wrong. Do something else. All right. So if you have, 10 degrees Celsius to 27, now your calculator will give you a wrong answer that you can write down. Your calculator will not give you a wrong answer for 0, because when you plug it in there, it will say undefined, you did something wrong. If you ever put in Celsius in a denominator, you always have the wrong answer. All right, so you must convert these to Kelvin, 273 Kelvin. All right, and then you have your 273.15 plus 27, that is 300 Kelvin. So V1, 79.4 milliliters. T1, 273 Kelvin. Volume 2, that's what we don't know. T2, 300 Kelvin. So some people can do this, but then they can't solve for V2. All right, you need to review basic math skills. Do not miss this because you don't know how to do basic math. You just multiply both sides by 300 Kelvin. That cancels that. Multiply both sides by 300 Kelvin. The Kelvin cancels the Kelvin. So you take 300 times 79.4 divided by 273. All right, again, your volume units can be any units. They just have to be the same. The temperature must be Kelvin. All right, if you put in Celsius, you will get the wrong answer every single time. 0 degrees Celsius won't even give you an answer. All right, and so when you push the buttons, okay, so we can look and we see we obtained this at 0. What would it be at a higher temperature? It is going to be larger than 79.4. And when you push the buttons, you will get 10% higher, 88-ish. 87.3 milliliters. All right, so again, your kelvins cancel, and then you have your volume in milliliters. When you have 3 sig figs and 3 sig figs and 3 sig figs, you give your answer to 3 sig figs. All right. Well, we skipped one. Why did we skip? All right, we won't skip it. We're going to do it here. All right, so then we're going to have Gay-Lussac's law. All right, so Gay-Lussac's law is a constant volume and constant moles. So the amount of gas is not going to change. So when I do Gay-Lussac's law, I put it into a piston, but I lock it. All right, and so the volume, whatever it is, let's say it's 1 liter, it is not going to change. And so I have locked my piston. So I'm trying to draw the same thing, not really working right. But anyway, so it's still 1 liter. All right, so we have it locked. The piston is locked. Constant volume, the gas volume is not going to change. If it's 1 liter here, it is 1 liter here. We locked our piston. All right, so what I'm going to do with this lock system is I'm going to get out a Bunsen burner and I'm going to heat this locked system. So here's my Bunsen burner making this thing very hot. Now, it depends on how good my piston is. If I reach a high enough pressure, it's going to explode. If I can get that pressure to be high enough in there to make my piston explode. All right, so this is a dangerous thing to do, heating a closed system. You can have a pressure burst. All right, so what's happening? Well, what's happening is I'm increasing my temperature by heating it with a Bunsen burner, and that is increasing my pressure, and if it gets high enough, it can explode. All right, I'm not changing the amount of gas. The same amount of gas is in here, same amount of gas is in here. The volume is the same. All right, so I have Gay-Lussac's law, which is a P1 over a T1 is equal to P2 over a T2. All right, so when you have these empirical gas laws, volume and pressure, they just have to be the same units. It makes no difference what they are, they just have to be the same. Again, you have your temperature and must be in Kelvin. All right, if you have a temperature, just T, and you can divide by that number, which is anytime you're multiplying and dividing, that T has to be in Kelvin because you can never divide by 0. It could never be in Celsius. All right, so if we have our pressure 1, let's say I'm at, let's say 1 atmosphere. 1.0 ATM. Well, we'll use 3 sig fig. 1.00 ATM. And temperature 1 is equal to 25 degrees Celsius. So basically, I have my piston in a room. Now I'm going to heat it up. It is then going to be heated. And so my temperature 2, I'm going to heat it until we are at, let's say 100 degrees Celsius. And then I want to know my P2. All right, so when I am doing this, I am going to get my units for P2 to be in atmospheres. So P1 is 1 ATM. My T1 is 25. No, do not put in 25. You would get the wrong answer. You must add 273.15. This is 298 Kelvin. Your P2, that's what we're looking for. What is the pressure after we heated this to 100 degrees Celsius? All right, again, do not put in 100. 273.15 is now 373.15. All right, so I am increasing my temperature because I am heating it, so I'm going to increase my pressure. My pressure is going to be higher than 1 atmosphere. And so I have to multiply both sides by 373.15. Just 373 to 3 sig figs. So 373, because no decimals here, 2 decimals, no decimals. 373 times 1 divided by 298, and we get a 1.25. So our pressure 2 is 1.25, and the units are the same as they are here, ATM. Again, you increase your temperature, you're going to increase your pressure. They are directly proportional. All right, so if you heat something that's closed, it will build up enough pressure that it could burst, right? Which is basically a tire. So you have your tire pressure, and then after you roll on the hot pavement, you are increasing the temperature, you're increasing the pressure inside of your tire, and if that pressure gets too high, you can have a tire blow out. Okay. All right, so now we can combine all 3 of our gas laws. And so we then have P1 V1 over T1 is equal to P2 V2 over T2. And what we have noticed for the first 3 gas laws is that we have a sample of gas that is constant. All right, so we have a constant amount of gas. So N is constant. N is the amount of gas in moles. So we are not injecting moles. We are not extracting moles of gas. We are not putting in more gas. We're not taking out gas. We are not doing that. We have the same amount of gas. What we're changing is pressure, volume, and temperatures. All right, so one thing has to be constant. If the temperature is constant, then we can eliminate this because we multiply whatever. If it was 100 Kelvin, again, if you multiply through by 100, it gets rid of that. There is no effect by putting the temperature in. All right, so then we have Boyles Law. If we had a constant pressure, so P1 is equal to P2, then we have V1 over T1, V2 over T2. We have Charles's Law. If we have a constant volume by locking our piston, all right, so then we have a pressure 1, temperature 1 over pressure 2, temperature 2. We have Gay-Lussac's Law. All right, so this equation for the combined gas law will answer any of those questions, but it will not answer the question whose law is this? Is this Boyle's Law, Charles' Law, Gay-Lussac's Law? You have to know the 3 different names, but this will answer all of those questions. So it doesn't matter if you put the same number in on both sides. It's not going to change your answer. But again, you have temperature in the denominator. Must be in Kelvin. All right, so pressure, volume just have to be the same units. All right, makes no difference what the units are for pressure and volume. They just have to be the same. Temperature must be in Kelvin. All right, so here is a question. We have a pressure. All right, so first pressure I get to, I call pressure 1, 5 times 10 to the first atmospheres at a depth of 5.0 times 10 to the second meters. If a balloon is inflated to a volume of 5 liters at that depth of water, at a water temperature of 4 degrees Celsius, what would the volume 2, what would the volume of the balloon be on the surface? The surface has a pressure 2 of 1 atmosphere at a temperature 2, of 11. All right, so we see that we have a different pressure. All right, we have a different temperature, and we're asking for the volume. And so we do not have constant pressure, we do not have constant volume, we do not have constant temperature. All right, they are all changing. So the only one that can solve this one is your P1 V1 over T1 is equal to P2 V2 over T2. All right, so we just put in our P1, 5.0 times 10 to the first ATM. We put in our V1, 5 liters. We put in our T1. This is where we have our trouble, okay? You can't put in 4. Plus 273.15, so you have a 277 Kelvin. All right, so these problems are very simple. They're also very simple to get wrong because a lot of people will put in 4 because they see temperature and they see a temperature, they plug it in. That is the wrong answer. So you must put it in Kelvin. All right, so what would the volume, okay, we don't know the volume, but P2 is 1 atmosphere at a volume of, that's what we're looking for, and 11. Again, if you put 4 and 11, the answer on your multiple choice, that one is there. It is the wrong answer. You add 273 to this, and it is 284 Kelvin. All right, so then you multiply both sides by 284, divide both sides by 1, and you get all right, so before we get this number, so what's happening? Our pressure is going down. All right, well, we're looking for a new volume, so we're starting at 5 liters. All right, so we are going from 50 atmospheres down to 1 atmosphere. So pressure is decreasing. All right, so when you decrease your pressure and your temperature is increasing. All right, so remember, if we had a constant, what is going to happen if we decrease our pressure? We decrease our pressure, we get a lot bigger volume. All right, so we would increase our volume. But our temperature is also increasing. So we went from a temperature of 273 to 284. And so an increase in temperature, remember what happens to the volume when you get hot, increases. This volume number better be a lot larger than the 5 liters. And it is a lot larger than the 5 liters. It is 2.6 times 10 to the second. All right, so this one only has 2 sig figs. This looks like it's 1 sig fig, but it's not. It is not 1 because when you take no decimals and add it to 2 decimals, you give your answer to no decimals, and this is 3 sig figs. This is also the same, well, it's 2 sig figs there, but when you add it to 273.15, now we have 3 sig figs. The reason why we have to give our answer to 2 sig figs is because this is 2 sig figs, this is 2 sig figs, and this is 2 sig figs. And so your answer has to be given to 2 sig figs. So the answer, it will come out on your calculator as 256 liters. You have to convert that to 2 sig figs by putting it in scientific notation. So again, you're giving your answer to 2 sig figs. So you had to convert it to scientific notation for that one to be correct to 2 sig figs. All right, Avogadro's law. So equal volumes of any 2 gases at the same temperature and pressure contain the same number of molecules. All right, and so what we're going to find for Avogadro's law is that if we have a reaction that is all gases, we can look at that in terms of moles, or we can look at that in terms of volumes. All right, so equal volumes of any 2 gases at the same temperature and pressure. So when we're doing a reaction in the lab, normally we're not going to, well, unless we're heating it up, if we're just on the lab bench, we would have the same pressure, same temperature. And so these could be used in terms of moles or in terms of a volume unit, most of the time liters, but any unit of volume. All right, and so a molar volume of gas. All right, so this is a constant at standard temperature and pressure. All right, so here's another thing that you have to memorize. So it's going to say STP. And you're going to say, what's the temperature and pressure? I'm going to say it's STP. You have to know that that is 0 degrees Celsius and 1 atmosphere. Anytime you see STP, your temperature is 0, your pressure is 1. All right, so it's just going to say at STP. You have to know that that means, great, I am at 273.15 Kelvin and 1 atmosphere. Exactly 0, exactly 1. So this is an infinite number of sig figs, not 1 sig fig. This is an infinite number of sig figs, not 1 sig fig. All right, but again, 0 Celsius is not very helpful with our gas laws. That's why I converted it to 273.15 Kelvin. Now, this is actually 5 sig figs. The 0 is perfect. So an infinite number of decimals plus 2 decimals, you give your answer to 2 decimals, so that is 5 sig figs. 1 atmosphere, perfect. You can put as many zeros after it as you need. So you can put, say, I don't know, 10. There you go. You'll never need more than 10. All right, whatever. That is not going to determine how many sig figs you give for your answer. All right, so the molar volume of a gas at STP is 22.4 liters per mole. All right, so if you have a balanced chemical reaction and you have 4 moles and you want to know how many liters that would be, well, you just multiply that by 4. All right, so that is a constant that doesn't need to be memorized. It can easily be calculated from PV is equal to nRT. All right, so that is your molar volume. That is the volume per mole. That is molar volume means volume per mole. All right, so that is the volume of 1 mole of gas. All right, so 1 mole of gas would be 22.4 liters. 2 moles of gas would be 44.8, et cetera, et cetera. So the molar volume just means what is your volume per mole at STP. You need to know what that means. It is 0 degrees Celsius in 1 atmosphere. The most common error for STP is putting in 25 degrees Celsius. STP 01. Make sure you write STP 01. 0 is the temperature in Celsius, and 1 is your pressure in atmospheres. Make sure that you not get the wrong temperature and pressure for STP, or you're going to have all the wrong answers. All right, so here are a bunch of R values. So here we have PV is equal to nRT. I promised the ideal gas equation, and there it is. All right, so for R calculations, we are always going to use this R value. All right, R values do not need to be memorized. If you need them, they will be given. You do not need to memorize your R values. All right, although this is given to 5 sig figs, I always give it to 4. 4 is always enough sig figs for, if you're giving more than 4, it could be right. Normally, 4 is as many as you're going to give. So I use 0.08206 liters times atmosphere per mole Kelvin. Again, you don't memorize this one. R values are constants. All constants are going to be given. All right, so that means, so you can use any of these R values, but this is the one that I'm always going to use. You can, again, convert all these different units if you want. Use whatever R value you want. These are all the same. These are all the same. They just have different units. So it's like saying, I don't want a kilogram of that. I want 1,000 grams of that. It's the same thing. All right, so these are all the same thing. They're just different units. All right, the reason why we're going to use this one is because we're going to have liters, so that means our volume must be in liters. All right, so when you had volume on 2 sides of the equation, they just had to be the same. When you use PV is equal to nRT and you only have 1 V, it has to be in liters because that is the R values unit for volume. Pressure. All right, you see here you have atmospheres, so pressure must be in atmospheres. Why does it have to be in atmospheres? Because that is what we are using for our constant R. All right, N is moles in all of these. One thing that these all have in constant is the denominator. They all are mole Kelvin. All right, so N is always in moles. N is moles, all right, and then your temperature in Kelvin. And that never changes in this chapter. Temperature always must be in Kelvin. All right. So again, you have a bunch of different R values. This is the one that we are always going to use for PV is equal to nRT, which is the ideal gas law, which means when you're using this, Whatever volume is given, you have to convert it to liters. Whatever pressure is given, you have to convert it to atmospheres. All right, you put varying amounts of a gas into a given container at a given temperature. Use the ideal gas to show the amount of moles of gas is proportional to the pressure at constant temperature and volume. So again, you simply have PV is equal to nRT, and you solve for N. So again, this is going to be, if you're really bad at math, you should definitely practice. This is very simple math. You should be able to solve for N. Many people are not able to do it. Maybe they skip steps. I don't know. If you're not an expert in math, you should not skip steps. All right, so when you are doing this, make sure you divide both sides by RT. You divide both sides by RT. So the R cancels the R, the T cancels the T. And you have PV over RT is equal to N. All right, so I would not skip steps. Whatever you do this side, you have to do to the other side. All right, and so then you'll get your PV over RT. And so if you are at a given temperature, what does that mean? That means your temperature is constant. All right. Into a given container, that means that your container is the same container, which means it has the same volume. All right. So same volume. So you have constant temperature, a given temperature, same container, same volume. All right, so you have a volume that is constant, you have a temperature is constant, and R is the ideal gas constant. All right, so your volume's a constant, your temperature is a constant, your R is a constant. So if you take constants and multiply and divide them, they are going to always give you the same number. Volume is always the same, R is always the same, T is always the same, and when you do this mathematical thing, it's always going to be the same number. So you take your volume divided by RT, it's always the same volume, it's always the same R value, it's always the same T. It always will give you the same answer when you push the buttons. And so N is directly proportional to your pressure, and it has this V over RT constant. So this is a gas in the same container, which means the same volume at a given temperature. We're not changing the temperatures. We're not sticking in an ice bath and then heating it up or anything like that. It's just sitting out in the lab at constant temperature. And so you see that your moles is proportional to your pressure. All right, so here is a question. You have a 50-liter cylinder of nitrogen. It is a volume. So your volume is 50 liters. All right, so that's your volume. We don't, when we do PV is equal to nRT, we don't have P1, V1, P2, V2. We don't have the twos. We just have, here's your volume, and it has a pressure. Here's your pressure. All right, so what's nice is they gave us our volume in liters, which is what it has to be in. They gave us our pressure in atmospheres, which it has to be in. All right, and like most, if not all the questions, the temperature is in Celsius, and we never want it to be in Celsius. All right, so you take your 273.15, you add your 23, you have a 296 Kelvin. All right, immediately convert all Celsius to Kelvin, or you will get the wrong answer. You'll do everything right except that, and that's going to give you the wrong answer every time. What is the mass of nitrogen in the cylinder? So you have PV is equal to nRT. All right, so for our molar mass, remember our molar mass is the mass over moles. So anytime you are needing a molar mass, you simply take the mass divided by moles. So M is your mass and N is your moles. All right, and so it asks for the mass of nitrogen in the cylinder. So it's asking for the mass. All right, so I'm going to do a substitution, and I'm going to solve for N here. So if I want N, all right, again, if you're not an expert in math, you should show all this work. You're multiplying both sides by N. Multiply both sides by N. That cancels. You divide both sides. Well, that's all you have to do. That is No, then you divide both sides by molar mass. We're solving for N. All right, so you take your mass and divide by your molar mass. To get moles, you take your mass and you divide by molar mass. So we can do a substitution. And so PV is equal to mass over molar mass RT. So we simply said N is equal to mass over molar mass, and we plugged it in for N. All right, and so we can then solve for a whole bunch of things, and one of them is mass. So if we want to solve for mass, again, multiply both sides by molar mass. All right, and so then we have to also get rid of this RT, divide both sides by RT. And so you get your mass is equal to your molar mass times pressure times volume divided by RT. All right, now again, this is N2. When you got nitrogen and it says mass of nitrogen, not an atom of nitrogen, but actual nitrogen gas. All right, so N2 is your molar mass. And so you plug in your numbers. So you have 28.02 grams per mole. All right, so you put in your 28.02 grams per mole. You put in your pressure, which gave it to you in the correct units, 17.1 atm. You plug in your volume, it gave you the correct units, 50 liters. Then you divide that by R. That's going to be given on the test. That is 0.08206 liters times atmospheres per mole Kelvin. And then your temperature that you immediately took your Celsius and converted to Kelvin. So you would not put in 23, you'll put in 296 Kelvin. All right, and so the liters cancel, denominator, numerator. Atmospheres cancel, denominator, numerator. All right, and then you have moles canceling moles, and you have your Kelvin canceling your Kelvin. And so then when you push the buttons, you have your answer for your mass. All right, so you plug in your 28.02 times 17.1 times 50 and divide that by 0.08206. And then you get that answer and divide by 296 and push the buttons and you get 3 sig figs. Yes. And so your mass is 986 grams. All right, so again, you could have just solved for moles, and once you had moles, convert that into mass. What I like to do is have all of my equations, and that will give me all of my equations. So there it is, solved for mass. Many times it'll ask, what is the identity of your gas? All right, and so your gas would then have a molar mass, and then you'd go to the periodic table and find out what that would be, what gas that would be. All right, so if we're solving for molar mass, and we come back up here, we would have that molar mass is equal to MRT over PV. All right, so if you have a question that says, what is the identity or what is the molar mass of this gas, you would be given a mass, R is a constant, temperature in Kelvin, pressure in atmospheres, volume in liters, and you would get your molar mass. Also note that density is mass over volume. And right here, we have mass over volume. All right, so you could find molar mass by taking the density, RT over V, RT over P. All right, so you could get, if they gave you the density and they asked for the molar mass, then you would just push the density and then times R times T over P, because mass over volume is the density. Note here that mass is in grams and volume is in liters. And so your density of a gas, all right, so just like we did density of solids and liquids, it was in grams per milliliter. When we're doing density of a gas, our units for this class are going to be grams per liter. So this is density for gases. It's always going to be in grams per liter for density of your gases. All right, you could also solve for density. All right, so if you solve that for density, let's say they wanted the density of this. All right, and so we'd have to multiply both sides by P. So you'd have your molar mass times your P divided by RT. All right, so this is all just a bunch of mathematical, and that is simply by taking PV is equal to nRT and substituting in for N your mass over your molar mass. So that went in right here. Once you have done that, you can solve for molar mass, you can solve for mass, you can solve for density. So there's a lot of different things that you can do once you do this substitution. All right. None of these equations are given. You must know all of these equations. Really, the only one you need to know is PV is equal to nRT and know how to find moles. You take moles, to get moles, you take your mass divided by your molar mass. Those are the two things you need to know. From that, you can get all of the other equations that you need. All right, so here it is on a slide. So they just go right to here's how you find density, and that's fine if you want to memorize it. I do not like to memorize stuff. I like to know things that I have to use all the time, and then I will get to stuff that I need later instead of memorizing a bunch of different equations. So here they are. You can just memorize them if you want, or you can get them by knowing how to find moles, because you have to know how to find moles. You get mass over your molar mass. You also must know PV is equal to nRT. And if you know these two things, you can get all of these different equations. Well, you also have to know density is the mass over the volume. All right, so you need to know all of those three things. That is for sure what you need to know. You do not need to memorize this and this because you can get that from those. All right, so what is the density of methane gas at 125 degrees Celsius? Again, 273.15. You would immediately write 398 Kelvin and 3.5 atmospheres. Again, the most common error. You know how to do it, but you do not change your temperature, and that is unfortunate because that gives you the wrong answer every time. All right, so again, if we go PV is equal to nRT, and I know that my moles is my mass divided by my molar mass. So PV is equal to mass over molar mass, RT. All right, and so I need to get my mass over my volume. I need my density. And so I have my molar mass times my pressure divided by RT is equal to the mass over the volume. All right, so anyway, you're going to get your density as molar mass times pressure divided by RT. And you should always put in your units. Make sure that you didn't mess up anything mathematically. If you put in your units, you will get the right units for your density, which is grams per liter. All right, so they tell us that it's methane gas, CH4. We need a molar mass. So 12.01 plus 4.04. This is a carbon. This is 4 H's. All right, 16.05 grams per mole is our molar mass. So you put in your 16.05 for your molar mass, grams per mole. The pressure has to be in atmospheres. It is 3.50 atmospheres. Your R value will be given. You write it down, 0.08206 liter atmosphere per mole Kelvin. Your temperature is in Celsius. You must convert that into Kelvin. And that is 398 Kelvin. All right, so then we can see that the atmospheres will cancel. All right, we also see that the moles are going to cancel. And we also see that our Kelvin is going to cancel. And we are left with grams in the numerator and liters in the denominator, which is our units for density. So when you take your 16.05 times 3.50 divided by 0.08206, and then divide that by 398 Kelvin. We get a density of 1.72 grams per liter for the density of methane gas. All right, so again, your units for density are always going to be grams per liter for gases. All right, we will pick up there tomorrow. Yes.